Hello, my name is Connor and I'll be presenting work with my advisor Ryan Farrell on improving fractal pre-training. Today's visual recognition models are pre-trained on huge datasets of natural images collected from various sources on the internet. These datasets have enabled deep learning models to become highly capable at many visual recognition tasks. However, they have some downsides. On the one hand, storing, transmitting, processing, and labeling these datasets can be challenging and costly. Furthermore, these datasets are often contain unfair bias, inappropriate content, or copyright images, issues that limit the application or use of the models trained on them. One potential way to circumvent the issues around large natural image datasets is to use synthetic, non-natural images for pre-training. With such data, many of the issues just mentioned become non-issues. In this work, we explore the use of synthetically generated fractal images as a source for pre-training visual recognition models. We build on recent work by Kataoka et al., which showed that a large set of generated fractal images can be used to successfully pre-train convolutional neural networks for image classification. The authors use a large set of randomly sampled affine iterated function systems as visual classes and train the model to classify them. This pre-training procedure produces features that are useful when fine-tuned on natural image domains. We extend the work of Kataoka et al. And make several improvements to their method, leading to pre-trained models that perform better on downstream natural image recognition tasks, particularly those with limited data. Our main contributions are as follows. We propose an efficient process for sampling well-behaved IFS codes using properties of the singular value decomposition. We modify the rendering process to include color and background textures. We show that we can generate all training images on the fly during training without requiring any offline image generation or storage. We propose a novel multi-instance prediction pre-training task that outperforms multi-class classification in downstream evaluation. In our approach, we first sample a set of IFS codes, which are used to define the dataset. We assign one or more IFS codes to a visual class for the purpose of training the model. During training, batches of images are rendered on the fly and fed to the network, which computes a loss and updates its parameters. After the model is trained, we fine-tune the pre-trained weights on natural image datasets. A 2D affine IFS is a set of two or more affine functions, each consisting of a linear transformation matrix and a translation vector with a total of 6 parameters. These parameters determine the shape of the resulting fractal. Sampling these parameters directly is inefficient, as many of the systems will violate the contractivity requirement of an IFS, leading to divergent systems that need to be rejected. We propose an approach based on the singular value decomposition that allows us to enforce contractivity during sampling so that every sampled system is usable. In addition, we find that issues of geometric sparsity or collapse in the fractals is highly correlated with a property of the singular values of the system, which we call the sigma factor, and we introduce an algorithm for sampling the singular values so that they respect sigma factor bounds and lead to more geometrically interesting fractal images. For training, we render our images in color using density information from the fractal iteration process. We also generate random background textures using the midpoint displacement technique. This leads to greater image diversity and more similarity to natural images. In order to avoid the overhead of generating and storing a large dataset offline for use in training, we develop an approach that generates all images on the fly during training. The key components of this approach are efficient code for generating images and a rendering cache for reusing computation. With sufficient CPU compute, we are able to generate images and train using multiple GPUs at speed. We also introduce a new multi-instance prediction task. For multi-instance prediction, we generate the images containing multiple fractals and treat each fractal class like a binary attribute. The model is trained using binary cross-entropy to predict the presence or absence of each fractal in each image. This task is much harder than normal multi-class classification and leads to pre-trained representations that perform better on natural image tasks. Our fractal pre-training produces models that, when fine-tuned on natural image tasks such as fine-grained recognition, consistently yield results much better than training from scratch, and in some cases achieve performance close to that of ImageNet pre-training, all while avoiding the pitfalls and hassles inherent in using large natural image datasets. For more details, we invite you to check out our paper and project website. Thank you.